This is the digital image processing lecture number 4. Today, I would like to talk about eye physiology, a conceptual technique for establishment of the model. Uh, and a model of the human visual system would perform the physiological analysis of the eye, the nerve paths to the brain, and those parts of the brain involved in visual concepts. Now, this picture shows the eye cross section. Later, I can show you in more detail. I will now discuss about each part. This figure shows the horizontal cross section of the human eyeballs. The front of the eye is covered by a transparent surface called cornea. This part. This part is cornea, and uh, by a transparent surface called cornea. Yeah. The remaining outer cover called sclera. Here is sclera. Yeah, it's hard part of the eye. It's composed of the fibrous coats that surrounded the co- co- choroid, a layer containing blood capillaries. Inside the choroid is retina. Inside retina is here. Retina is here. Here is which is composed of two types of the receptors, rods and cones. Rods and cones. Nerves connected to the retina, nerves connected to the retina here. Leaves the eyeball through the optical nerve bundle. Light entering the cornea is focused on the retina surface by a lens that changes shape under the muscular control to perform proper focusing of the near and distance objects. So this muscle, change the lens shape, push or pull it, and to light enter into the cornea, focus on the surface of the by lens that change the shape under the muscular control of the performance focus of the near and far side. And iris acts as a diaphragm. Iris. This is iris. It's like diaphragm. It's colorful of the eye. The iris acts as a diaphragm to control the amount of the light entering the eye. So it is like blue or blue color, black or brown color, something like that. Okay. So this is the structure of the eye. So we have cornea here, we have lens here, we have sclera here. This is this white part of the body of the eye, and the retina, and the blood vessel, and the muscular and iris. An eye contains about 6.5 million cones and 100 million rods. So number of the cone is 6.5 million, but number of rods is 100 million. It's distributed like this over the retina. Over the retina, this is retina. So if you open this eye from minus 80 degree to plus 80 degree, you see that the rod and cones are distributed like this. This is, for instance, zero angle, minus 80 to plus 80 degree, and this is rod, and this is the cone. Cones are more concentrated on the center here of the eye. This is figure 2. Shows the distribution of the rod and cone over the horizontal line of the retina. At the point near the optic nerve, is optic nerve here, called fovea. This is fovea. The density of the cone is greater. Here is fovea, and density is here is fovea, and density is highest. This reason is sharpest optical vision. There are not rods or cones in vicinity of the optic nerve. In fovea is maximum, but in vicinity of this is the nerve, and hence the eye has a blind spot in this region. So here is blind spot, so no cell or no nerve or no, or I mean, horns or rods are here. So we have, this is blood spot here, because here is the optical nerve. There are no rods or cone in the vicinity of the optical nerve, and hence the eye has a blind spot in this region. So here is the distribution of the rod like this. This is the distribution of the cone. This. I will tell later that rods are responsible for the brightness of the sun, and cones are responsible for taking the color. So color at the center is more sensing in the center. Here near fovea, the color is maximum. But here, the less cones, so less color is sensed here, but more color sensed here. This is very important. I will show this later. The lens contains 60 to 70% of water, 6% of fats. That these fats with the age gets yellowish, and that is the in eye ophthalmology they call it cataract. So if the old person after taking a lot of ultraviolet to the lens, the water no fat, the fat gets yellowish and then become like cataract. We call it cataract, and it is like a white falls, and people cannot see very well. In this case, the surgery very easily, I will show you here, very easily uh, separate, I mean, very easily cut this lens and suck the uh, liquid inside this hydraulic membranes. I mean, this side, the liquid suck the liquid, and instead they put a artificial lens here that the sight is better, more cleaner and better. So this is cataract operation that physician they do this in age, for instance, 50, 60, or 70. It depends how much ultraviolet eyes can receive. The second, the iris diaphragm control the amount of the light that entered the eye, the eyes. This is very important. So when it's brighter, the iris gets closer. It's like diaphragm in the camera, and it resembles the color of the eye. For instance, if it is blue or green or black or brown. So we see in the bright light. But in the night light, it open totally. So you will see only the retina or inside the eye, which is almost black. Three light receptor in the retina. In retina, there are light receptor. I told you codes and rods. About 6 to 7 million cones for bright light vision called photo optic, and the density of the cone is 150. This is per square millimeter. 150,000 millimeters. So here, number of the cones is 5 million total, but in the in each square millimeter is 150,000. It's like the digital camera, but much more higher. The density of the element is much more higher than the present digital camera of today. Cone involved in color vision that I told you that is responsible to take the color, red, green, blue, something like that. So cone are very important, which is concentrated near fovea, 150,000 per square millimeter. Cones are concentrated in fovea about this 1.5 millimeter. So it is very dense. Here I show you again. Here is very dense here, but as we go farther from fovea, it is reduced. Density of cones are reduced. And about 75 to 150 million compared with 6 to 7 roads. So the number of roads are very high for dim lights, very small light vision called scotopic. Roads are sensitive to low level of light and are not involved in color vision. So this part of the eye has higher road, this part, or here, even here, and here. There are more roads here, so even here you can sense the, here of course you can less, here is less anyway, this in this, but no, but in the fovea there are less, but anyway, here is the very high level of the road, so that's why you, the, it can sense the dim light, so not the color. Low level light and not moving color. Blind spot is region of emerging of the optical nerve from the eye. So that's why blood, we call it blind spots. Okay. There is some phenomena which are visual phenomena. Here is like this. It is kind of delta I to I. It's like derivative of the logarithm. So that's why this delta I to I is constant in the intensity of the normal intensity. Very low intensity or very high intensity of the light, it's different. But the level of delta I to I is almost 2% for detecting the some, for instance, we have a surface with the intensity I, and we have a circle with intensity of I plus delta I. So delta I, the ratio between delta I to I is the logarithmic ratio sensing of the light, which is constant in not very dark, not very bright. In normal light, it's almost 2%. So around 2%, less than 2%, you cannot sense. The circle cannot be sensed. More than 2%, it can sense this circle. The response of the eye to change in intensity of the illumination is known to be nonlinear. This is nonlinear. That's why it's nonlinear. Consider the patch of the light of intensity surrounded by a black intensity eye. Just notice difference is to be determined as a function of the eye over a wide range of the intensity. It is found that the ratio called Weber. This ratio called Weber ratio. Weber fraction. Weber fraction is near constant, which is equals 0.022%. So for different ones, so you can see that this is the sensitivity of the eye difference, the Weber fraction of Weber ratio. Also, we define MTF here. MTF is the modulation transfer function, is the we previously I talked about the Fourier transform of the input and output. The ratio of the magnitude of the Fourier transform of the input and output. Here is output, the Fourier transform of the output. For instance, this is the response of the eye. For the output is the sense, and input is input of this. So Fourier transform ratio between output to input, we call it the impulse response, or anyway, the response of the eye to different spatial frequency of omega x and omega y. So horizontal and vertical. So here we have a vertical line with higher frequency as x increase. So here is low frequency, here is high frequency. This is a spatial space domain frequency. So as we can see, we have the more sensitivity in the middle and low sensitivity at the higher. So it's like this, almost like this. This is called modulation transfer function, MTF, of the optical system. So the ability of measurement of the human visual system by module sine wave rating. So MTF is important in a sense here. And also, as you know, the lens is inverting this cell that you see, and the retina is reversed, but automatically brain can adjust it that this way that they see, and it's like this. the dimension. For instance, is 100 meter. This only eye is 17 millimeter, and this is the image. Near side for near side focus. So when it is near side, so it adjusts by change of the dimension of the lens. The normal side and far side is the changing the also the muscular, the pressure of the muscular here and less pressure here. So the lens for far side focus, and you can see this is farther, so you can, if it is on retina, you can see. Unless otherwise you don't need the glasses. And here I'm talking about the Mach band here. I think see something different here. Brightness of adaptation of human eye. This is Mach band effect. Mach band effect is like this. For instance, you have the picture like this, which is a step function like this, from dark to white here. Actually, the steps are increasing gradually like this with flat. This is flat area. This is dropping the intensity. So this is a vertical line is intense. This is the position of the horizontal line here. So gradually from black to white is increased the brightness. But now what we see is here is a little bit, here is brighter than here is brighter than here, and so on. So you can see that for middle step, human eyes can separate better than the lower or higher step. So here is more separatable, the steps are more separatable than higher and lower. This is Mach band. Also, you can see here, for instance, in area A, because it's white, brightness perceived is darker. It seems darker than here. While in the area of B, because it's black, here is brighter than here. So this is Mach band effect. Mach band effect. And so response with response of position, density is gradually increased like this. So this is important. Also, you can see here the same simultaneous contrast. So here, the level of the brightness is the same, but it depends on the surrounding. If surrounding is too dark, you see more bright. If it is more bright, you see more dark. All the smallest circle are exactly the same intensity, but they appear progressive darker as background become lighter. So the background become lighter, so it is darker. But actually, this inner square is a same, like this, same level of darkness, like this also. And in electromagnetic wave, this is the energy of the photon of electron. For here is 10 to the power 6 from 10 to minus 6, and frequency is 10 to the power 21, 10 to the power 5, frequency in hertz. So here is kilo mega, this is mega, this is giga, this is tera. And what we can, the wavelength is here, from 10 to power minus 12 to 10 to power 3. So for radio wave are here, radio waves are here, and hard X-ray is here, ultraviolet is here, infrared is here. Only our eye can recognize very small portion of here between visible spectrum is between around 10 to power minus 6. 10 to power minus 6 from 0.4 multiplied by 10 minus 6. This is wavelengths, of course, in meter. This is violet to 0.7 to 10 to power minus 6. This is milli micrometer. 10 to 1 minus 6 is micrometer. It is red. So from violet, then blue, green, yellow, orange, and red. So gradually, wavelengths increase here, rather frequency decreases, but in very narrow side. So this is hard extends ultraviolet, visible spectrum, infrared, and radio wave are here. And in gamma ray and soft X-ray, and this microwave of here. It is electromagnetic spectrum because light is also electromagnetic wave, so that's why we say visible spectrum is shown. Zoom facilitates explanation, but not the visible spectrum is rather narrow portion of the electromagnet. From till here, I will next I stop here. I think better I stop this lecture number 4, and then for next time we go to the single sensor, line sensor, and array sensor for digital image sensor typically used in digital camera. In digital camera, you see the number of the sensor or cell are much more bigger than the actual human eyes. So light is here, energy is here, the filter and power and sensing, and then there is voltage here. So it's actually in digital camera, what happened is one cell is here. So it is array cell like this, image sensor. This single sensor, this is line sensor, and this is array sensor. And this image sensor typically used in digital camera. You can see the more expensive camera has higher array sensor and number of the cell are more cells here. So here I think. So also we can see, for instance, at the, for simplicity, I can see here is a sensor, and this is here. And then, for instance, for an example here, we can also continue here. This original image after storm, and this is one pixel is we call it f of xy. So this coordinate x and coordinate y. At this point, the level of the intensity is f. An image, a multidimensional function of the spatial coordinate. Spatial coordinate xy for two-dimensional case such as photographic, and three dimensions such as CT scan image. Three dimension is X, Y, Z, like a scan of the brain and so on. And for 4D is like movie or TV, X, Y, and Z. The function F may represent the intensity of monochrome image that can be color for color image for this association. Digital image and image has been discretized. Also discretized, we discretize the image in a spatial coordinate and associated value. Consider the two-step, one point of the set and two the value of the set. Also, this is the x with the this one, also an element of the X for the pixel. So each one is a pixel. For instance, the smallest one here, each one is a pixel. And here, for instance, you have the X, Y, and the number. For instance, we have N horizontal pixel, N vertical pixel, and M multiplied by N is the number of pixels that, for instance, defined for image or for digital camera. And the number and the fxy is the brightness level of the light on each pixel at the each coordinate. For instance, the intensity of the image for monochrome is like this. This is each pixel correspond to the light intensity. As soon I will finish this part, but it's extended a little bit, but I wanted to finish earlier. Light represent a gray level. So here, if we expand this part, it's becoming, and this part is this. So here you can see gray scale of this part is, with this matrix is 10, 10, 16, 19, something like this, and with this. So this is the dimension for 4 by 4 matrix. For color image RGB, we have, for instance, this circle here, that circle, this square here, and then inside this square, much more smaller square, and then there is blue, green, red. The measure of the RGB component is this, then you can see the color. Also for binary image, we have black and white, 1 and 0, especially in homomorphic imaging, we have this binary, and also it's like facts also. Black and white. Black is 0, white is 1. Binary image. Also, index image represent the index image pointed for color image. We have red, green, blue, the level of the red, green, and we have index. For each index represent the, for instance, for this square, we have 166. This is the index value. So this is the address of the points. Each address, they represent the level of the green, blue, red, green. So if it is 1, it's here. If it is 4, it's here. If it is 9, it should be here, or 6, 5 is this one. So this is 4. This is the address, and this is the data represent the color index image, for instance, for each pixel. And this is the, as I said, this is sense, this is image sensing and internal image, and then this is the digital image. And this is for one line of A to B. We have different from white here to black, and then gradually getting lighter here, and then getting darker here, and then getting white here. So it is, if it is for this line, we have this the horizontal, this is scanning line, and then there are different level of the brightness, and this is each one is quantized in different level like this, that later I will explain. For instance, this is the image sampling. So it's if the sample is more than less discretization is seen, so it's a spatial domain. A spatial domain represents the resolution of the image size of pixel. And we have this sampling of the image. And also we have for each pixel, we have quantization that I will show you later here, like this, for instance. If it is, this is for sampling, spatial resolution. This was spatial resolution original, and if it is high sample, you can recognize. Low sample, you cannot recognize. So it is sample. About the sample, you can say the Nyquist rate here. We have also, it's like the sclera processing. We have Nyquist rates. So Nyquist rates also here. It's possible to define about the where is this point, where is this point, so we can find the very clear if the frequency of sampling is higher. This is Nyquist rate. And then here is different 256 multiplied by 2 by 6 pixel. This is 128 by 128. And gradually, if the less sample, then gradually you have the kind of the mosaic effect. Mosaic effect. For instance, 30 by 32 by 32 is more visible, 64 also, but 128 and 256 maybe more sample, but maybe is redundant. Then this effect of we have another effect here that I will explain later about down sampling, and this is, for instance, for sampling and low sampling and high sampling here, and about quantization is here. Yeah, this is about the quantizations. And the next one is about the sampling, digital image. So in next number 5, I will explain that these two effects of the quantization and sampling are maybe the number of the bit per pixel is same, but the effect is different. For instance, this is the level of the 256 of quantization. This is 32 quantization. We can see the false coloring, false contouring here because of low digitization of two sample here. And then for middle, so we have different levels. I will next time I will explain more for medium detail of image activities, medium or low activity and high activity. So gradually the sense of the sensing line is, become more vertical. This I will explain later in next video. I will explain more in detail. And here, number 4 finished. Thank you very much. I stop here.